All right. So we're gonna be doing an improv stream where I'm going to be solving problems, LeetCode problems, and I'm gonna try to verbalize my thought process so that we can learn how to tackle the problems. So let's start by choosing, hello smart coder, welcome. Let's start choosing some easies to get started, to warm up. Hello creepypasto, welcome as well. I can't complain. I'm just gonna be solving some problems. So minimum, let me share the link if you want to check it out. A bit flip, so minimum bit flips to convert number. Bit flip, choosing a bit in the binary representation of x and flipping it to either 0 to 1 or 1 to 0. So it is what we would expect. Here we get an example. So 7 has this binary representation, 1, 1, 1. We'll take the statement's word for it. We may choose any bit, including any leading zeros not shown, and flip it. So that's important. We can flip the first bit from the right to get this. All right, so given two integers, start and goal, return the minimum number of bit flips to convert start to goal. All right. We have two examples. All right, so let's think about it a little bit. So seems like we can just go over all the bit positions in any order and see if they are different. And in that case, we need a flip to make them equal. So that seems to be the approach. Also, my tablet wasn't ready. Let me set it up. Oh, so I think it is ready now. See, yes. So we are, let's say we have this number. So how are the numbers? So we have start. So let's say this is start. And this is goal. And so yes, I think the idea of going in any order, considering the bits and checking whether there's a difference. So I'm thinking now if there is a way, because we can do this by looping over all the positions, but maybe there's a way to do it with a bitwise operator that already counts. So if you think about it, well, maybe here I'm making a leap, but here we are doing a toggle, and there is a relationship between flipping or toggling bits with the XOR operation. You don't need to know that in advance, but it seems like the XOR bitwise operator might be useful here. So how do we investigate if it is if it is useful. So whenever you want to do bitwise operators, you can use a truth table and consider all the possible. So yeah, let me check something because my tablet is not correctly configured, I think. Let me check it out. Okay. Okay, so we have, let's say we have 2 bits, and we want then to check the XOR. So what are all the combinations? We can have 0, 0, we can have 0, 1, or 1, 0, or 1, 1. Those are all the combinations. Maybe you've done this before in school. And notice that the XOR is 1 only when they are different. These 2 cases. The other cases you get 0. So that means that if we do an XOR of this, which is, we're going to get a 1. So here they are the same. We're going to get a 0. We're going to get a 1 only in the bits that are different in all of them. So that means that if we do the XOR, then we only need to count the ones on the result to know how many we needed to flip. And that's going to be our answer. So in Python, to count the number of 1 bits, there is, I think it's called bit count. So we want to do start XOR goal, and then we want to call bit count of the result, and that should give us the answer. Yes, it works for the examples. And it passes. So the code is pretty simple, as you can see. But it requires some thinking. But that's what we're here for. We could have done this without using the bitwise. So this operator is processing all the bits in the same operation. We thought about, so this is a strategy that is common when you are considering bits of a number. You're considering the binary representation. It often is productive to think about every bit independently, like we did here, because in that case there are usually, so in this case there were only 4 possibilities. So if you consider only 1 bit or 1 position in this case, which included the bit for X and the bit for Y, or start and goal if you want, then the problem becomes very small. So that's one way of solving problems, trying to manage the complexity, reduce it into small, very small independent problems. doing a simplification in a sense. And then we reduce this to counting the number of ones, which we had a function in Python. We can do it without that as well. There are several things, but we might. I mean, if you're interested, I can dive into it, but I don't think it's necessary right now. So let's move on to a second problem. Let me share it. Minimum number of operations to convert time. All right. So time sometimes can be scary because there are a lot of irregularities related to time. But let's see. We are given two strings, current and correct, representing two 24-hour times. 24-hour times are formatted as this way, this format. And where are we doing ISIS? So you think you're a Bob ISIS smart coder? I said I was warming up. I'm improvising. This is a different kind of stream. But I'm trying to give a very detailed description of the thought process to solve the ISIS, and maybe go over different strategies, maybe even try to solve it in a faster way. Usually ISIS can be solved with brute force, but you can also solve them faster, and then they become harder. But yeah, we might then start with some mediums or some hards, whatever you want. If you have a problem request, I can consider it. Anyway, so okay, so this is the format. It's a usual 24-hour time. Cool. Well, you would never figure that out. Well, you should think about stealing ideas, if you will. So now that you learned this idea, I explain how I broke this down, of thinking of each bit independently, and that's how we arrived at this. So yeah, maybe some intuition that I had was I already knew that XOR is related to flipping bits. That's why I try the XOR operator from the get-go. But it was not necessary to solve this problem. So I think this is called the Hamming distance. In information theory, Hamming distance between two strings of equal length is the number of positions at which the corresponding symbols are different. So there's a lot. As usual, you can dive very deeply on even the easiest problems. So for example, for binary strings A and B, the Hamming distance is equal to the number of ones in A XOR B. So that's what we did. I did not cheat it. I did not remember this. I just so yes, this is essentially the Hamming distance for binary, for strings with two possible symbols on each position. Anyway, so convert time. So we get the format of a time of the day. In one operation, we can increase the time current by this number of minutes. You can perform this operation any number of times. Return the minimum number of operations needed to convert current to correct. Okay, this doesn't sound trivial. Doesn't sound trivial. So one observation here, which is interesting, is that all these numbers are multiples. They are a chain of multiples if you think about it, because 60 is a multiple of 15, and 15 is a multiple of 5, and 5 is a multiple of 1. So that seems relevant, because we can try to first go over, try to get as close as we can by increasing the minutes. Well, the 6 by 60 minutes, and then the remainder by 15, and then the remainder by 5, and then by 1. And that should give us the minimum number. So one strategy for dealing with this kind of time format is to convert it to the number of minutes from the beginning of the day, from zero. So that reduces the complexity of dealing with hours and minutes and maybe seconds. So if you can count the minimum unit, it simplifies dealing with times. So are we guaranteed that one? Yes, current is less than correct. So that is interesting. So yeah, let's start by doing a translate. So we get a string, and we are going to do this. Hours and minutes are going to be splitting by this, and we want to map the int function to convert them, and each hour has 6 minutes, so that's going to give us the number of minutes from the start of the day. So now we can translate current, and we can make this a problem about numbers and not about times this way. Okay, so this is also a very common strategy for solving problems, is trying to change the representation, translate the input into a better representation to solve a problem, and sometimes losing irrelevant information. So it is a kind of lossy compression of the information in the input. So, and also I think we do not even need to keep them both, because we care about the delta, the difference. Yeah, let's call it difference. So that is what we need. And so then we're going to go from the divisors in order. So they are 60, 15, 5, and 1. I don't think I need this. And then we can we use div mod of this? So Q and R, we want this, and that means that we are going to need this many apply the jumps for this number Q times, and then diff is going to be now the reminder. Is that correct? Yeah, so we need to jump as many times as we can. So that means that we want to divide diff, which is how much we need to jump in total, by d, which is the jump size, the jump length. So these are the number of complete jumps that we can do without exceeding diff, and then this is going to be the reminder. Yeah, I guess it's pretty clean. Thank you. So then we add how many full jumps we did, and we update diff with the reminder. So is that correct? Yes, because yes, I think this is correct. So it passes the examples, and it's good. 90% almost. So it's pretty cool. So I think if this property is not true, the property of this being a chain of multiples, then it might be the case. So this is similar to the coin change problem, right? Because this, you can think about the diff of an amount of money, and these are the different coins denominations that you have, and you want to give the change for this amount. And I think if this is true, that they are all American coin change, well, that's what I'm saying. The types of coins, if they are a chain of multiples, then you can use this greedy algorithm of getting as many as you can of the biggest, and then as many as you can of the second biggest, and so on. But if that's not true, then the greedy choice does not work necessarily. So you need to do some dynamic programming. So it is interesting that you see this problem that is uneasy. It's so I don't think this is so easy, because you need to conjecture yes, if 1, 2, 5, so 2 is not a divisor of 5, and that's why it doesn't satisfy the condition that I'm saying. But yeah, I was saying this is not really that easy because you need to conjecture that you can do this greedily. And okay, you can do that intuitively and try it out, and it works, but it's not that trivial to prove it. Okay, so it's an interesting problem. So don't underestimate the easies, because sometimes you can go deeper and understand some more general concepts by trying to decompose them and generalize them and connect them with other types of problems. So okay, so we have solved this two, the first two. So let's keep going in order. I just chose a random page and I filtered by easies. And so I wanted to check more recent problems because I think they are better, but not the latest, because those are the ones from the latest contest that I have been doing. So I want problems that I haven't solved before. Largest number after digit swaps by parity. Add to integers sounds like a very boring problem about, well. Hey, Reggie, thanks for the follow. So what is it? Given to return the sum of the two integers. What is the catch? What the fuck? There is no catch, and the numbers are even small. What is this problem? No, I'm gonna. Bit solution. But it didn't say that you needed to, it didn't say any restriction. Anyway, so, oh, you mean the first one that we did, anyways, I'm not following. So find the closest number to 0. Given an integer array, return the number with the value closest to 0. There are multiple answers. Return the number with the largest. Okay, so this is an optimization kind of problem. We want a minimum. So what are we gonna do? So we are going to use in Python the min function, right? So we want to consider, the values in nums, but in order to implement the tie break condition, we need to we're gonna need to be creative with the key. So we first want the minimum value, the minimum distance to 0. So distance is always in the integers, it's always computed with the abs function. So that's going to give us the minimum. But then if we have tie breaks, we want the largest value. But this is a minimum, so we can change the sign so that the minimum becomes the maximum. What does meta thinking means? That's an excellent question. It means thinking about thinking. And that is that I'm trying to think about how I'm thinking the problems and explain it so that we can learn to improve our strategies to solve problems and not just to solve a particular problem. So that is the idea. Okay. So, and again, so we are asked to find a minimum, but there is a tie-break condition. So we consider all the values, but then we're going to use this key to compare them, which implements the criteria described here. So that's going to be it. And it works. Easy peasy. And it's 89%. It beats 89% of users with Python 3, so that's cool. So can we do this better? Faster? Well, no. If the numbers don't have any order, then we have to get the minimum. We have to go over all of them, because if we skipped one, that could be the answer. But if there was some condition about if they were sorted in some way, then maybe we could do something faster, but that's not the case in this problem. So let's move on. Did we open another one? No. So we are 3 problems. Wait, explain the lambda with an example. The lambda, you mean the this strategy of negating the number so that the maximum becomes the minimum. So, well, you can think about, I never use lambda for mean function, so I can't comprehend. So yeah, there is this, so in many functions where you have to define an order in Python, you get this optional parameter, which is the key, which is a function that, given an element, it gives you some value that is comparable, and that it's going to be used to compare the elements and either sort them or get the minimum or the maximum, or even doing a binary search and so on. And so the lambda has to receive one of the elements in the list and give you something that it can be compared. And here we decided to first, so this criteria first tries to compare by the distance to 0, which is implemented by the abs function, because if you have n or minus n, then you can cancel the negative sign, and that's going to give you the distance to 0. But this is the trick. The trick is that since we're asked to tie break with the largest value, but we're using the mean, so the mean will try to get them compared by this element, and if they are the same, it's going to get the minimum of this element, but we want the maximum. That's why we change. So another way to do this will be to have a regular function for, well, a key function. So it doesn't have to be a lambda. So the lambda gives you anonymous function. So we can have this here and then just do it this way. No, it's not doing a sort. Yeah, this is key. It's not doing a sort. No. Sort is slow. We don't to get the minimum. We only it is comparing. So how do you get the minimum? You keep track of the minimum so far. You go over all the elements and you compare them with the current minimum and you update it accordingly. So this is using the key function to compare them, to update the minimum. Sorting is n log n, but getting the minimum or the maximum is linear, is O of n. So it's not the same thing. You shouldn't, or in interviews, you shouldn't. So, hey, Warden, how's it going? So mean is storing the mean so far value. That's nuts. Oh, I mean, that's a way that also we could implement this, right? We could, my min will be, so we get an array and we get a key function and we get the mean so far, which is none. We go over all the elements, and if the key of E is less than the key of the mean so far, then we update the mean so far with E, and that's all there is to it. So now we call my mean, and yeah, we have so I guess we could use inf here and it will work. Right. So yeah, it's not nuts. It's pretty it's what you would do. So this is how the key is used. So I hope it's clear. Root equals sum of children. Okay, a root. What's that? Is a square root? Oh no, it's the root of a binary tree. You're given the root of a binary tree and consists of exactly 3 nodes. So it's just a 3-node binary tree. Turn true if the value of the root is equal to the sum of the value of 2 children. So yeah, this one is a little, what the heck? So what is the, so yeah, I guess when they are over 80%, they are too easy. Yes, I'm not gonna do this one. Sorry. Largest number after digit swaps by parity. So you're given, you swap 2 digits. Yeah, but then you start getting, well, I guess we can do that. Do you really want that? I can choose from this list the ones that have the lowest. So I can do the sorting with my eyes by looking at it, doing a sequential search. We can find the minimum just like we did with the function. Anyway, so have the same parity, both odd digits. Well, that is interesting, but how do we deal with 0 and leading zeros? That's my first question. Oh, so they don't explain that. That's silly. So I guess so you're trying to get the largest, so it's never gonna be the case that you wanna swap 0 with the most significant digit. Yeah, I will do. Thanks for watching. See you tomorrow. Good luck. Okay, so here we have to, so if we can swap, so you may swap any 2 digits. So we can do only, so any number of swaps. Okay, so that means that we have to consider the places where there are even digits, and we can sort that from largest to smallest, and then we can do the same for the odd digits. And again, we sort them from largest to smallest. So how do we do that? That's interesting. How do we do that? Efficiently. Or not efficiently, but with simple code. So we're gonna do a sort, or 2 sorts, actually. So, juice, meat, a sort of sorts. Is that a pun? So juice, welcome. I missed your question. I haven't checked your GitHub homepage. Anyway, so yes, I'm thinking of having. Yeah, I haven't checked it out either. I can do that later. So is there anything in particular that you think it's interesting? So let's go over the digits, the decimal digits of n. And let's have a So let's group them by their parity. Let's group them by their parity, and we also need to keep their position. Or let's remember the parity for each thing. So this is the digit, right? So if it is, so let's keep track of the parity. And also let's add it to the group for that parity. Then we want to, for each group in groups, we want them to sort them in reverse order. And then we want to go, we want to generate the result. And for that, we're going to go, yes, P in the parity, but this is, so we appended, so we want to go from the most significant. So let's go over it in the reverse order. So this is the parity of the most significant digit. Or yeah, then let's not do it this way. Let's sort them in order so that we can pop from the biggest to the smallest. So then what do we do here? We want res, we want to shift it, and then we want to add the current digit. But this is going to be from the group of the corresponding parity, and we want to pop because that's going to give us the largest element, and that's going to be it. Oh, so this is num, so let's change it. So the parameter is wrong, not my code. And int object, so oh, so this is groups, not group. Accepted, well, not accepted, sorry. So let's add one case where there are zeros, just in case we mess it up. Exactly. You got them right. All right. And accepted. Okay. Did anyone follow what I did here? I don't know if this is the simplest way to do this. I guess another approach would be to turn into strings and do more of more of well, I guess it's the same. So yeah, I think this is solid. This makes sense to me, at least. So one more problem. We have 4 so far. That's cool. What else? So you wanted one with low percentage. Yeah, let's keep going in order and skipping the ones that are too easy. Oh, this has a long statement. Consisting of digits of an integer k. A round can be completed if the length of s is greater than k. In one round, do the following. Divide s into consecutive groups of size k, such that the first k characters are in the first group, and so on. The size of the last group can be smaller than k. Okay. Replace each group of s with the string representing the sum of all its digits. For example, is replaced by 13 because this is 10 and 13. All right. Merge consecutive to form a new string. If the length of the string is greater than k, repeat from step 1. Okay, so this has just simulation written all over it. So yes, at each step, So a group is going to be of size k, right? So k is at most 100. And there are up to 100 digits. Yeah, I think we just need to do this. And that's the end of it. So how can we do this easily? So, well, the structure of our code is going to be, so this means if length is greater than k, we're going to do a round, and if it's not, we return s, okay? So a round is going to be, so the start, it's going to be from the beginning, so from 0 to the length of s, and jumping k times, and then we're going to map this to s from start, and from start plus k, and we're gonna add the digits, and that's going to give us so this is going to be the next S, and we're going to append this to the next S, and then we want to join and we want to map this to strings, and we want to join them, and that's going to be the next S, and that's all there is to it. And that's it. All right, easy. So yes, I did this. So here I'm just, so yeah, the first idea here is let's simulate this process. Okay, so there are only the length is only 100, so it seems like it's going to take so every time we iterate, we do a round, S should decrease in size. So it seems like we're gonna do at most, as an upper bound, 100 iterations. So that's okay. And the condition here is that here's the condition: if the length of S, which is what we wrote here, while this is true, otherwise we return S. And here, so another way of writing this would be so iterate S and we also need to know K, and we just return this, and so this becomes this, which is very simple, but it boils down the structure of this simulation. And then here we're doing the two loop kind of solution. So this loop is not explicit in Python. We're doing this slice, and then we're iterating with this, with map and sum. And we're appending each group to the next S. And then we are concatenating all of them after we transform them into strings. And so yeah, I think this is clear. Oh yeah, I forgot to pass K here. All right. Intersection of multiple arrays. That one sounds boring. So you want to move up to medium, maybe. But let's go to more recent problems. Count number of bad pairs. let's see if we can do this one. You are given a zero index integer array nums, a pair of indices. I, j is bad if So what does this mean? So the difference in terms of value is the same as the difference in terms of indices. Interesting. So this sounds like a two-sum kind of problem. So maybe we can go over j and then try to count how many i's there are that satisfy the condition. And how would we count that quickly? So, well, let's first confirm that we have to do it fast. Well, yeah, we cannot go over all the pairs. So let's say that we know j and nums of j, or let's call it n of j. So we want to find all of this all the pairs that satisfy this condition, but we already know this. So we can change this equation into this. So this is a constant, right? And then we want all the values that have this constant as the difference between their position and their value. So we can keep track of, we can count how many there are for each of these differences to the left of j, and that is going to give us how many i's there are for a given j. And that's all there is to it. So here, Smart Coder, we are going over the mediums, and they're not being very hard, to be honest. I don't want to brag, but this one's not very hard. So we want the nums of j. So this is the value, and we want to add how many there are. We call this constant. Well, x is okay. Let's call it d of difference. And so we want to know how many there are with the same difference. And then we want to add that difference. And that is it. So here, we got 1. So, oh, let's see how this is. So 0 and 2 is that, oh, so yeah, it's the other way. Oh, so we have to count the okay, this is easy. Len of nums. So then we just count all the pairs and we subtract the bad pairs. Okay. Cool. So I guess another way to write this is to put it here and then subtract here. And this should also work. So this is the number of total pairs of n elements. So we are counting the bad pairs, but we're asked to count the non-bad pairs. So that's why we subtract the bad pairs from the total pairs. That's going to give us the non-bad pairs as they ask us. So yeah, smart coder, this is not hard. I'm sorry to tell you. No, I'm just kidding. So yeah, it's been an hour and 10 minutes. I'm gonna end the stream now. And I'm gonna continue tomorrow. And we'll see if I do one of the more prepared streams, or if I keep doing this style of more improvise and trying to be very explicit about my thought process, so that we can try to learn what the best strategies to tackle problems are. So thank you for watching and see you tomorrow. Bye bye.